Now, I have already alluded to this, how work and energy are the same thing, and that's completely true. It's called the work-energy theorem. Whenever you do work on an object, it's going to gain energy, or if the object's doing work, it's going to lose potential energy. Both of them have the same unit, the unit of the joule. Energy has a unit of the joule, and work has the unit of the joule, capital J, right? So something to remember there, that they're the exact same thing. Now, if you were doing work on something, so you were giving energy to it because you're doing work on it, it's going to gain kinetic energy. It's going to end up, and that's going to translate into a gain in velocity. So here's a quick little easy example problem. I have a 1,000-kilogram car. And the car's engine is going to do work on that car, applying 10,000 newtons over the course of 20 meters. And so the question is, how fast does this car get going if the engine's applying a 10,000 newton force to this 1,000-kilogram car? Now, you could try to go back to F equals ma. You could go through all of that. And then, so you do F equals ma to find acceleration and then kinematics, or you could just use work-energy theorem. So here I went ahead and set up our work-energy theorem. Work equals change in kinetic energy, because that's what the engine is doing. It's doing work on the car, thus making the car gain speed. And so the way to think about this is just simply energy input, energy output. So whenever you get a problem and you want to use work-energy theorem and you think it might work, just simply think, where is the energy coming from? Where is it going into? The energy is coming from here, the work done by the car's engine, and it's going to go into making the car speed up. Kinetic energy, that's why I set work equal to delta KE, and then whenever I write my equations in, F delta X equals 1/2 mv delta V squared, because we're going to change velocity. We can't say necessarily that the initial velocity is going to be 0. Notice also on the work side, F delta X, I dropped off the cosine theta, force times displacement cosine theta, because I know that the force the engine is exerting is forward and the distance is forward. So the cosine theta is not even needed. So I divide by my 1/2 m, trying to get delta V by itself here. And then, by the way, dividing by half, same thing as multiplying by 2. That's why dividing by half, that 2 then goes to the numerator. Take the square root of both sides. Then I'm going to make the assumption that the initial velocity was 0. So that means final velocity. If there was some initial velocity, you just add it over here. And so there's everything in letter format now that we just plug in numbers. And I come out with 20 meters per second. Now, another interesting thing here, by the way, these two things are exactly the same. If you'd break it down here, I'll just kind of show this on this part of the equation. F, right, is mass times acceleration, so you'd break your F into ma, and then your acceleration is delta V over t, right, change in velocity divided by time. And whenever you do that, you can combine some things, and you'll see that the two sides come out to be the same. Maybe we'll do that in class. Now, if you're instead talking about potential energy, work done by a conservative force is equal to the negative change in potential energy. Here's the best way I find to think about that. Here's the Earth, and here's an object above the Earth, and so the force of gravity is pulling it downwards. Whatever work gravity does, and gravity is a conservative force, whatever work gravity does on the object actually decreases, thus the negative, decreases the potential energy of the object. Make sure you write down what a conservative force is. The definition of a conservative force is any force that is independent of path. In other words, for this object over here, it doesn't matter how I get from this first ring to the second ring, nor where along this ring I am. I can go all sorts of crazy ways, but if I end up here, it doesn't matter if I did it just like that or if I just went straight down to that point. It is path independent. That's gravity. It doesn't matter how far up and down you go. Maybe you do some positive work, then some negative work, then some positive work, and it all cancels out. Friction isn't a conservative force. That's a prime example, because then every step counts, because the further you go, that's further friction has to act on the object. So that would be a non-conservative force. Anyway, work, if we're talking about if we're talking about a conservative force doing work on an object, it is going to take away your potential energy. That's if the conservative force is doing the work. I'm going to do an example problem where you're doing the work and giving it potential energy. More on that. You can also then, if you'd like to, reverse this around like I did over here. Work is the same thing as the integral of f dx, right? Dropping the cosine theta here, assuming the same direction, and that's equal to negative potential energy. So then that becomes taking the derivative of both sides to get rid of that integral. Now I have du. Divide by your dx, and that says the force that is being exerted, a conservative force, is equal to the negative change in potential energy according to position, dx. All right, let's try to apply these things rapidly in a few slides. Now we're going to do a simple problem involving a rocket launching off, and we're not looking to have any kinetic energy left over. We're just looking for the rocket to gain potential energy all the way up to 100 kilometers above the Earth's surface. Now, our equation, work equals negative potential energy, negative U. That applies whenever we're dealing with the conservative force, specifically in this case, gravity. The amount of work gravity does, pulling the rocket down, is going to cause a loss in potential energy. Here, though, we're not actually dealing with the gravity pulling it down. We're dealing with the amount of work the rocket's engines are doing to lift it up, which is going to cause a gain in potential energy. If you ever are getting confused about positives and negatives, it's really very simple. Just simply ask, where's the energy coming from and what is it trying to do? Here, the rocket engines, the work done by the rocket engines is where it's coming from, and it's trying to cause a gain in potential energy. So work equals U here. Now, whenever I break that down, work, force times the displacement, here delta y, cosine theta, but I know that both of them are aligned, so work is just force times displacement, cosine theta, theta 0. So delta y going up, and gravitational potential energy is mgh. Now, big disclaimer here. mgh actually wouldn't technically work for this problem because this 100 kilometers away is so far away that actually our g, 9.81, is going to change on us. So we would need to use Newton's universal law of gravitation, but I haven't taught you that yet, so we're going to make this approximation just mgh here. Also of note, this delta y and h are different, specifically because whenever a rocket burns, it's going to accelerate as long as it has fuel. And then after it's done accelerating, right, after it runs out of fuel, I shouldn't have coast written here, it should be decelerating, right, because then gravity is going to slow it down and it'll eventually reach a maximum height where velocity is going to end up equaling 0. Up there, final velocity would end up equaling 0 all the way at the top. Now, if you were working this with just kinematics and Newton's second law, you would have multiple pieces. You'd do the acceleration piece, F equals ma. You'd figure out how far it goes there. You'd figure out how long it takes. Then you'd take that velocity of the acceleration piece, carry it into the next piece, and the deceleration piece with gravity. You've solved a problem just like that. Add up the two displacements over the two distances. The beauty of this problem is that's not needed anymore. Delta y is how long the force is acting. mgh, h is the final height it reaches. So I can actually plug in, and I'm solving for h here because I'm solving for y. How far must the rocket's engines burn? H is the final height we're trying to get up to, and those two aren't necessarily the same. Whenever I work this all the way through, I come out with 39 kilometers. Don't forget here, this 100 kilometers for the height that we're trying to get up to here. That's 100 kilometers. That's kilometers times 10 to the third there, and then converting back to kilometers just because it makes it a nicer number. I actually need to go in here. This 100 kilometers only has one sig fig, so I'm going to give myself a decimal there. That way I get to be controlled by my two sig figs in that number. All of these energy problems are very, very straightforward. All you have to think about is where's the energy coming from and where is it going. Here's another problem that you have solved in the past using F equals ma. I've got a ball that rolls down a hill, and we can approximate a hill to be a ramp like I did down here, and I'm telling you the hypotenuse of that ramp, if you will, and the height of that ramp, 12 meters, and then the question is how fast will the ball be going at the bottom. Now, the way you've done that in the past is you would draw a free body diagram, you would tilt the axis, right, mg sine theta goes down the ramp, you got force of friction going back up the ramp, since this does include friction. It tells me what the average force here is. By the way, that's very nice that friction went ahead and told you the average force instead of telling you mu, which would have been fine. You could have used mu. And then you end up finding the acceleration, and then you use kinematics to get the final velocity at the bottom of the hill. But using conservation of energy and work energy theorem makes it much, much easier. The trick here is to remember that work is just another type of energy. Work and energy are the same thing. So the question here is, what type of energy does the ball have in the beginning? Where's the energy coming from? And the answer is it starts out with potential energy up at the top. Where does the energy go? Well, over the course of the hill, it's converted into work done by friction and kinetic energy. So those are the two places that it goes into. And I really shouldn't write PE. I want to go ahead and get used to writing U here for us. So it starts out as potential energy and gets converted into kinetic energy of the ball, and friction does some work on it as well. Now remember, work and energy are scalars. The unit joules. It doesn't matter which direction these are going. It's all just energy. The only thing that matters, though, is with work that the force and the displacement are lined up at all times. Otherwise, you got to use that cosine theta to get them aligned. But here, work done by friction is pointing back up the ramp, and the displacement's pointing down the ramp. In other words, it's going to work out. So here I've got gravitational potential energy, I've got kinetic energy, and I have work done by friction on the final side, because that's one of the spots that the energy is going to. Now you might say, hey, the work done by friction actually should be negative because the force is pointing back up the ramp and the displacement's coming down the ramp. Yes, it should. That's why it's on the final side with the kinetic energy. That takes care of it for me, because I'm just saying where is the energy going. Starts out at potential and goes into these things. I find that's a much easier way to think about it. Where does the energy come from? Where does it go to? Also, notice how the masses do not cancel out here. I do not have mass in every single term. I only have it in these two, but not in the work done by friction, so I cannot cancel out mass like we used to in conservation of energy. So now I'm going to solve for final velocity here, because that's the goal. How fast will the ball be going at the bottom of the hill? So I'm going to solve for it all in letters and then substitute numbers in. And I end up coming out with significant figures, 12 meters per second. Do remember that if solving all this through in letter format, which I think is much better, if that makes you nervous, then you can start plugging in numbers. You could start plugging in numbers right here and simplifying down to where you don't have as many terms that you're working with. Simply do whatever makes you the most comfortable that's going to make it easier for you to do these problems. All right, so now let's look at this just using some very simple calculus terms. I've got an object that is experiencing a force given by the graph and that equation there. And my question here is, what's the final velocity of this 500 kilogram object after 3 seconds? Right, so in this area here, I remember under a force displacement graph, the area under a force displacement graph is the work, aka the integral of a force displacement equation, or of a force, is going to give me, according to displacement, is going to give me the work done. And work is equal to kinetic energy. The work that an object does on something is equal to how much kinetic energy it gains. So here, the integral of f dx equals 1/2 mv squared. And I should say change in velocity squared. I believe I've dropped that off in the last problem there, which is a big no-no there, because it ends up assuming that the initial velocity was 0, which might not be the case. That change in velocity is actually final minus initial. So I went ahead and substituted in my numbers now, and I'm going to go ahead and take the integral there of the left-hand side from 0 to 3, because that's the displacements we care about. Now I'm using some weird notation there just to make sure we remember integrals 0.5 over 4, because whenever I take the integral, the exponent goes up, right, in power rules, so the x to the third becomes x to the fourth, and then I have to send that to the denominator, and so I'm purposefully trying to show that 0.5 divided by 4, and I'm going to evaluate that between 0 and 3 now. And I come out, if I assume two significant figures, 0.30, I would have to change around my equation here and my graph to where I had two significant figures. I had 3 here, but I only gave myself 1 there. A few things of note. Whenever I substitute 0 in, then the entire thing becomes 0, thus the minus 0 here. Also, I made an assumption that the initial velocity was 0. That's why delta v just changed into final velocity. Now to do a few quick proofs dealing with springs. An equation that you need to write down. Force of a spring is equal to negative kx. Now that negative is very important. What that indicates is a spring always pulls the opposite way it's displaced. Quick picture of this idea. If you displace a spring to the right, then it makes sense that the force goes back to the left. That's what the negative sign means. The displacement and the force are always opposite. K there is just simply a constant. That's called the spring constant. And X is obviously how far you stretch or compress the spring. And so that equation's given. Please write that equation down. You could see that equation show up in another Newton's second law problem somewhere, or something dealing with forces where instead an object's on a spring. We're going to deal with springs more this year. Derive the equation for potential energy of a spring. Now remember, work is equal to negative potential energy. So to get from a force equation to potential energy, let's use work. Work is the integral f dx if it's all going the exact same direction. I'm going to start it out at some initial position, x naught, and end at some final position, x. So substituting that in, now remember k is a constant, so whenever I take that integral, this x just goes up to x squared, right? So I'm going to have negative kx squared, negative 1/2 kx squared. Remember, got to send that 2 down to the denominator here. And so then I'm going to come out substituting everything in. Negative 1/2 kx squared minus 1/2 kx naught squared. Factor out the negative 1/2 k. And then obviously both sides are negative, so then we can multiply both sides by -1 and get rid of it. All right, let's work that in reverse. By the way, there should be a 1/2 right there, of course. I'm going to go from potential energy of a spring back into the force on the spring. Now remember here, work equals negative u. That also means, we derived earlier, force equals negative du dx. So now I just need to take the derivative of the function. I'm going to leave the negative outside there. It's going to get applied here at the very end. So the derivative of 1/2 k, in parentheses, x squared minus x naught squared. Remember, the 1/2 k and the x naught are all constants. The only thing that isn't a constant is the x. And derivative of any constant is 0, so that part just goes away. So I'm going to end up taking the 2 here, multiplying it down, right? And this is going to completely go away. And then I'm back to my original equation. Force of a spring equals negative kx.